Okay, so for the next video here, we're looking at the equation for determining the strength of the magnetic field. And that equation is written right here. And what it is that if you have multiple loops, then N is the number of loops or turns of the coil inside the solenoid, and mu naught is from the data booklet, so it's the permeability of free space. It's the 4 pi times 10 to the negative 7 value. I, capital I, is current in amps, and L is length of the solenoid in meters. All right, so how can you intensify a solenoid's magnetic field, making it much stronger? Well, this can be done by putting a soft iron core, which could be just a nail made out of iron, inside the solenoid. And when this occurs, all the domains inside the iron core, and you'll learn what a domain is in a moment, will align with the magnetic field created by the solenoid and amplify and strengthen this magnetic field. So let's look at what a domain is. Well, to understand a domain, you first have to understand why iron, cobalt, and nickel are the only elements on the periodic table, and they're all beside each other on the periodic table, that are magnetic. And the reason that these atoms are magnetic is because when electrons spin, so if we look at this diagram right here, one second. So if we look at this diagram right here, you can see that electrons actually spin around, and if you use your 4 fingers and curl around in the direction, your 4 fingers, curl them around in the direction of the spin, then you have to use your left hand when you do this. Why? Because electrons are negatively charged. So you always use your left hand for negatively charged particles. And when you do that, you discover that your thumb's pointing down towards north. And when the electron spins in the opposite direction, which is shown in the next diagram, then you're going to get the north pointing up. Now, most atoms have the same number of, and they call this upspin and downspin. So this would have been a downspin, this right beside it. Let's see if I can get this to... So this one would be an upspin, this one would be a downspin. And most atoms have the same number of upspin and downspin electrons inside of them. You need at least 4 or 5 upspin, more upspin than downspin electrons in order for an atom to be magnetic. And when you're looking at iron, cobalt, and nickel, they all have either 4 to 5 more upspin electrons than downspin, creating a net overall magnetic field for that atom. And we say that that atom has a magnetic dipole. There's a north and a south pole to that atom. So when we're looking at domains, I'll need to show you the diagram on the next page. When you're looking at domains, all they are is when you've got several dipoles or several atoms of iron all pointing in the same direction. So there might be 1,000 atoms all aligned up in one direction in that section of the iron. In another section of the iron, all the north poles of the iron atoms will be oriented in another direction. And in another section, they're in yet another direction. And as you know, most pieces of iron are not magnetic. And the reason they're not magnetic is because all these domains are in different directions. So if you have a domain pointing in this direction and then in another, the opposite direction in another part of that iron, they're going to cancel each other. If they're pointing something, a domain's pointing in this direction and then in the opposite direction in another part, they're going to cancel. And so you don't have an overall magnetic field to that piece of iron. But if you can get all the domains to line up in the same direction inside a piece of iron, you can turn it into a magnet. So, why is most iron not magnetic? The domains are randomized. They cancel each other. They're not aligned in the same direction. How can you turn them into permanent magnets? Well, if you were to take any piece of iron, cobalt, or nickel and rub a permanent magnet always in the same direction, lifting it up when you got to the end and holding it up high and then bringing it down on the other end and then dragging it always in the same direction, you will you will permanently align that and create a magnet. So you could take even a needle, like a sewing needle, and if you take a permanent magnet, always rubbing in the same direction, you'll turn that into that little needle into a magnet. So what do the words soft iron core mean? Because we're going to be talking about placing a soft iron core inside the solenoid. Soft iron is just pure iron with no impurities. Soft iron, the domains can be temporarily lined up, just like how you see them in this image. And you can create a temporary magnet when you've aligned all those fields, and they can get aligned like this due to the solenoids magnetic field. So if you place this iron core right here inside a solenoid, the solenoid will create a magnetic field that all of these domains will line up with. And they will only line up when the electric current is flowing through the solenoid and the solenoid's creating that magnetic field. The minute you turn off that electric current, it will return to its randomized state and no longer be magnetic. And this is how an electromagnet works. So what happens, though, if you used carbon steel instead of soft iron? Well, you'd align the domains, but then they would never return to their randomized state, and you'd actually have created a permanent magnet. So you can't put carbon steel in to an electromagnet, because essentially the minute that you turn that electricity on, you've now created a permanent magnet, and when you cut the electricity, you don't turn off the magnet. and whatever gets stuck to the electromagnet will just stay stuck to it. And with electromagnets, what you want to ideally be able to do is turn on the electricity, create a magnet, lift up a car in a scrapyard, take it to a new location, cut the power, and then all of a sudden there's no magnet anymore and the car drops in the new location that you wanted to put it in. So electromagnets are really handy because you can just turn on the electric power, turn it off, magnet turns on and off. Now describe the parts and explain how an electromagnet works. So when the current passes through the solenoid, a uniform magnetic field is created inside the solenoid. The domains in the soft iron core align with the field, amplifying it. When the current is cut, the domains randomize again, and the magnetic field disappears, dissipates, no more. All right, there's a diagram showing how this occurs. All right, now questions. So we'll start that in the next video.